Welcome to Understand the Math. In this Calculus 1 video, we're learning about hyperbolic functions, which are similar to trigonometric functions, but are defined using exponential functions. We'll start by introducing the definitions of the 6 hyperbolic functions and walk through some examples. Then we'll look at key identities and formulas, learn how to differentiate hyperbolic functions, and then finish with examples involving inverse hyperbolic functions. Be sure to download the free guided notes to follow along and work through the examples with me. Let's begin by going over the 6 hyperbolic function definitions and walk through some examples. Hyperbolic functions are actually really similar to trigonometric functions. In this graph, I have drawn the unit circle, x squared plus y squared is equal to 1, and then I've also drawn the hyperbola, x squared minus y squared is equal to 1. As you know from trigonometry, trigonometric functions describe the coordinates of points on the unit circle. Here's the point, defined by cosine x and sine x. And then hyperbolic functions describe the coordinates of points on a hyperbola. Here's one of the points on the hyperbola, and its point is given by the hyperbolic function cosh²x, sech²x. There are 6 hyperbolic functions, and they're defined in terms of exponential functions. The hyperbolic sine function is written as sech²x, and you can see that it's defined in terms of exponentials. The hyperbolic cosine is cosh²x, and it's also defined in terms of exponentials. The difference between these two functions is with the sinh function, there's a minus sign, but with the cosh function, there is a positive sign. The really nice thing about the other 4 hyperbolic functions is they can be defined just like trigonometric functions are defined. The hyperbolic tangent function is tanh²x, and it's sech² over cosh²x. The hyperbolic cosecant function can be pronounced as cosech²x, and it's just 1 over sech²x. The hyperbolic secant function is sech²x, and it's just 1 over cosh. And then lastly, the hyperbolic cotangent function is coth²x, and it's just cosh² over sech²x. Down here at the bottom, I have graphed sech² and then cosh² so that you can see what they look like. We are going to find the numerical value of each expression. Our first example is sech²0. We are going to evaluate this by starting with the definition. We know that sech² is equal to e to the x minus e to the minus x, all divided by 2. So now we're just going to let x be equal to 0. So we have sech² is just e to the 0 minus e to the minus 0, all over 2. So this is just 1 minus 1 over 2, and it's equal to 0. Now let's look at our second example. We are going to evaluate cosh²0. Again, we're going to start with the definition. Cosh² is equal to e to the x plus e to the minus x over 2. There's a plus in this one instead of a minus, like with the sech. Now we're going to substitute in that x is 0. So this is e to the 0 plus e to the minus 0, all over 2. And this gives us 1 plus 1 over 2, and we get a value of 1. In our third example, we are going to evaluate sech²1. Sech² is e to the x minus e to the minus x. I'm going to save space here and write it like that. Now we're going to substitute in that x is equal to 1. So we get e to the 1 minus e to the minus 1 over 2. This is just equal to e minus 1 over e, all divided by 2. And when you put that in your calculator, you get a value of 1.1752. This is the exact answer, and then this is the approximate answer. Let's now look at number 4. It is very similar to number 3. We are going to be evaluating cosh of 1. We'll start by writing down the definition of cosh. Cosh of x is e to the x plus e to the minus x, all divided by 2. Now we're going to substitute in that x is equal to 1, and we get e plus e to the minus 1 divided by 2. This is just e plus 1 over e, all divided by 2. And this is approximately 1.5431. Here's our exact answer. And then this is our approximate answer. Let's now look at number 5. We are going to evaluate tanh of 1. Tanh of x is sinh of x, all divided by cosh of x. Very similar to our trig function, tangent is equal to sine over cosine. Now we're going to plug in what sech is. So this is e to the x minus e to the minus x divided by 2. And then cosh is the same thing, but there is a plus. So we have e to the x plus e to the minus x divided by 2. The 2's cancel each other out. And now we can go ahead and let x be equal to 1. So we have tanh of 1 is e to the 1 minus e to the minus 1, all divided by e to the 1 plus e to the minus 1. We can write this a little nicer as e minus 1 over e, all divided by e plus 1 over e. And that is approximately 0.7616. Here is our exact answer, and then this is our approximate answer. We're now going to go over some important hyperbolic function identities and formulas, and then walk through some proofs. The identity that relates cosh and sech is cosh² minus sinh² is equal to 1. And then tanh is related to sech by 1 minus tanh² is equal to sech²x. And then we have a formula for sech of x plus y and cosh of x plus y. Those 4 formulas are similar to the trig function formulas, but the signs are different. Up here in the upper right, we have a formula for sech of minus x, and it's just minus sech of x. And then cosh of minus x is just cosh of x. Now, those 2 formulas are the same as the formulas that you have for sine and cosine. Let's now walk through some examples where we are going to prove the given identity. The first identity that we're going to prove is cosh² minus sech² is equal to 1. The way that we're going to prove this identity is we are going to write down the definitions for cosh and sech, and then we're going to substitute them in. Cosh of x is e to the x plus e to the minus x, all divided by 2. And then sech of x is e to the x minus e to the minus x, all divided by 2. This gives us cosh² minus sech² is equal to our first exponential expression, e to the x plus e to the minus x, all divided by 2 squared. And then we subtract off our second term that is squared. So this is e to the x minus e to the minus x, all divided by 2, and that gets squared. Now we are going to square both of those terms. When you have two terms that are added and you square it, what you do is you square the first term. So this is e to the x times e to the x. And then you add 2 times the first term times the second term. And then you square your second term. So that gives us a plus e to the minus x times e to the minus x. And then down below we have 2 squared. So we're going to divide this by 4. Now we're going to do the same thing for the second term. And we're going to subtract that off. So we have in the second term e to the x times e to the x. Now for the middle term, we have a negative. So we have a minus 2 e to the x times e to the minus x. And then our last term, we have a minus e to the minus x squared. So that becomes a plus e to the minus x times e to the minus x. And then that is divided by 4. Now let's go ahead and simplify. E to the x times e to the x is e to the 2x. And then we have plus 2 because e to the x times e to the minus x is e to the 0, which is just 1. And then we pick up a plus e to the minus 2x. Now for our second expression, we have to realize that we have a minus in front, so we're going to have to subtract off every term. So this is minus e to the 2x. And then we have a minus 2, so that gives us a plus 2. And then our last term is minus e to the minus 2x. And all of this is divided by 4. Now let's go ahead and let's see what cancels. Our e to the 2x cancels. And then our e to the minus 2x cancels. So it looks like we are going to get 1 because we have a 4 on top and a 4 on the bottom, and that gives us a value of 1. So we have proven that cosh²x minus sinh²x is equal to 1. Let's now look at number 2. We need to prove that sech of minus x is equal to minus sech of x. Let's start with the definition. We know that sech of x is equal to e to the x minus e to the minus x, all divided by 2. Whenever you're doing proofs, you always want to start with the more complicated side. In this proof, the more complicated side is sech of minus x. So let's write down what sech of minus x is. And then we'll simplify it to be minus sech of x. Sech of minus x is just e to the minus x minus e to the minus x, all divided by 2. So this is e to the minus x minus e to the x, all divided by 2. We can take out a negative. We take out that negative, we end up with e to the x minus e to the minus x. So this is looking good. And we divide that by 2. We then know that e to the x minus e to the minus x is just sech²x. So we have proven that sech of minus x is minus sech of x. Let's go ahead and let's highlight this. Sech of minus x is minus sech of x. In example 3, we are going to prove the formula that sech of x plus y is sech(x) cosh y plus cosh(x) times sech y. We always want to start with the more complicated side when you do a proof. So we are going to start with the right-hand side. Just to get us started, I am going to write down the definitions that we're going to need. Sech of x is e to the x minus e to the minus x, all divided by 2. And then cosh of x is e to the x plus e to the minus x, all divided by 2. Now what we're going to do is write down what sech(x) cosh² plus cosh² sinh² is equal to. Sinh of x is e to the x minus e to the minus x, all divided by 2. Now we're going to find cosh of y. So we look up at our formula up here on the right for cosh(x), but now we're going to put a y in instead of an x. So this is just e to the y plus e to the minus y all over 2. And now we're going to plug in what cosh(x) is. Now we're going to use an x, so this is e to the x plus e to the minus x, all divided by 2. And then lastly, we have sinh of y, and this is e to the y minus e to the minus y, all divided by 2. Now we get to multiply all this out. Let's first multiply this term times this term, and then we'll divide it by 4. We are going to use the FOIL method. The FOIL method, I'm going to write over here, F-O-I-L. So we're going to multiply the first terms, and that is e to the x times e to the y. So we're going to add the exponents and get x plus y. Then we're going to multiply the outer terms, and this gives us a plus e to the x minus y. Now we're going to multiply the inner terms, so this is minus e to the minus x plus y. And then lastly, we're going to multiply the last terms, which is minus e to the minus x minus y. And then all of that gets divided by 4. Now we're going to multiply this term times this term. So we're going to add the first term's multiplied, so this is e to the x plus y. And then we're going to multiply our outer terms, which is minus e to the x minus y. And then the inner terms, which is plus e to the minus x plus y. And then lastly, the last terms, which is minus e to the minus x minus y. And all of that is also divided by 4. Now let's see which of these terms is going to cancel. This term cancels with this term, and this term cancels with this term. And let's see what we have left. This term and this term are the same. So this is 2e to the x plus y. And then this term and this term are the same. So this is minus 2e to the minus x minus y. And all of this gets divided by 4. We can divide by 2. And then I'm also going to pull out a negative from that term right there. So this gives us e to the x plus y minus e to the minus x plus y, all divided by 2. Now we have a function that looks like sinh. This term and this term are the same, so this is just sinh of x plus y. And this is exactly what we had up here on our left-hand side. Let's now see how to take derivatives of hyperbolic functions, and then we'll walk through some examples. The really great thing about derivatives of hyperbolic functions is that they are almost identical to the derivatives of trigonometric functions. Down here, I have listed the derivative of sinh, tanh, and sech, and then cosh, coth, and cosech. 5 of these are the same as our trig function derivatives, and the one that's different is this one right here. The derivative of cosh of x is sinh of x instead of minus sinh of x. Let's now walk through some examples where we are going to find the derivative. Our first example is the function f of x is sinh of x squared. Let's remind ourselves that the derivative with respect to x of sinh of x is cosh of x. Notice in this example that we have an x squared in here. So we are going to have to use the chain rule. F prime of x is the derivative of the outer function, which is our sech function. So the derivative of sech is cosh. So we have cosh x squared. And then we have to multiply by the derivative of what's inside. The derivative of x squared is 2x. So we're going to write our answer as 2x cosh of x squared. And let's go ahead and highlight that. Let's now look at our second example. F of x is sech² of x. I am going to first rewrite this as f of x is equal to the quantity sech² squared. When we see it written like that, we can know that we are going to have to use the power rule to take the derivative. Our derivative, f prime of x, is going to be 2 because you just bring down that exponent. And then we have sech of x times the derivative of sech, and the derivative of sech is cosh. So we have a cosh x. So our answer is 2 sech x times cosh x. Let's now look at example 3. I wanted to include a problem where we had to use the product rule. So I made this example, f of x is e to the x times cosh of x. E to the x is our first function, and then cosh x is our second function. Our derivative then, using the product rule, is the first function, e to the x, times the derivative of the second function. And before we do that, let's write the derivative here of cosh. The derivative of cosh x is positive sech x. Now let's go ahead and go back. We are taking the derivative of cosh, so that is sech x, and then we're going to add the second function, which is our cosh x, times the derivative of the first. The derivative of e to the x is just e to the x. Now, if we look at this, we can see that both of our terms have an e to the x common, so we can pull that out, and we can write this as e to the x times sech x plus cosh x. And that's our final answer. We are going to learn about inverse hyperbolic functions and then walk through some examples. Since hyperbolic functions are defined in terms of exponential functions, inverse hyperbolic functions are defined in terms of logarithms. I have written down the definition of inverse sinh of x, inverse cosh of x, and inverse tanh of x. All three of these definitions have logarithms in them. And then one thing to note with these definitions is that each of these functions has different domains. Inverse sinh of x is defined for every value of x. Inverse cosh of x, because of that square root of x squared minus 1, is only defined if x is greater than or equal to 1. And then inverse tanh of x is defined between minus 1 and 1, and that's because what's inside our logarithm here has to be greater than 0. Let's now walk through some examples where we are going to find the numerical value of each of the given expressions. The first expression that we're given is inverse sinh of 1. Let's start by writing down the formula for inverse sinh of x. Inverse sinh of x is the natural log of x plus the square root of x squared plus 1. Now what we're going to do is we're going to take x and let it be equal to 1. So we have inverse sinh of 1 is natural log of 1 plus the square root of 1 plus 1. And this is the natural log of 1 plus the square root of 2. If you put that into your calculator, you get an approximate value of 0.8814. This is our exact answer, and then this is the approximate answer. Now we have a really similar example for number 2. We are going to evaluate inverse cosh of 1. Let's begin by writing down the formula. Inverse cosh of x is the natural log of x plus the square root of x squared minus 1. Now we're going to let x be equal to 1. So we have inverse cosh of 1. This is natural log of 1 plus the square root of 1 minus 1. So we end up with natural log of 1. Natural log of 1 is equal to 0. Now let's look at our third example. We are going to evaluate inverse tanh of 0. Let's write down our formula first. Inverse tanh of x is 1/2 times the natural log of 1 plus x, all divided by 1 minus x. Now let's let x be equal to 0. So we have inverse tanh of 0. This is 1/2 natural log of just 1 plus 0. So we have a 1 on top, and then we have a 1 on the bottom. So this is 1/2 natural log of 1. Natural log of 1 is 0, so our answer is just equal to 0. Let's now look at how to find the derivatives of inverse hyperbolic functions. These formulas are different than the derivatives of inverse trigonometric functions. I've written down the derivative of inverse sinh²x, inverse sech²x, inverse tanh²x. Sometimes I feel like those are really hard to say. And then inverse cosh²x, inverse cosh²x, and then lastly, inverse coth of x. Before we walk through our examples, I want to call your attention to this formula and this formula. Those two derivatives are the same, and that might seem a little strange, but it works out because the derivative of inverse tanh of x is only defined for absolute value x less than 1, and then the derivative of inverse coth of x is only defined for absolute value x greater than 1. Let's now walk through some examples where we're going to use these formulas to find the derivative of the given function. The first function that we're given is f of x is equal to inverse sinh of tangent x. Let's begin by writing down the formula for the derivative with respect to x of inverse sinh of x. That is equal to 1 all divided by the square root of 1 plus x squared. We are going to need to use the chain rule because we have an outer function and an inner function. Our derivative f prime of x is the derivative of the outer function. That is 1 divided by the square root of 1 plus x squared. X is what is ever inside, and in this example, what is inside is tangent, so we have a tangent squared x in our square root. And then we have to multiply this by the derivative of what's inside. The derivative of tangent is secant squared x. Now we can go ahead and do some simplification. We have an identity that tells us that 1 plus tangent squared x is secant squared x. So in our square root, we're going to put in secant squared instead of 1 plus tangent squared. So we have the square root of secant²x times secant²x. So one of our secants is going to cancel, and we end up with just an answer of secant x. Let's now look at our second example. We are going to find the derivative of inverse cosh of the square root of x. Again, we are going to use the chain rule because we have an outer function and then we have an inner function. Let's first write down what our derivative is. The derivative with respect to x of inverse cosh² is 1 all divided by the square root of x² minus 1. Our derivative f prime of x is then 1 all divided by the square root. Our x is now root x, so we have the square root of x quantity squared minus 1 times the derivative of root x. So let's just write this as the derivative with respect to x, and we'll write root x as x to the 1/2. Our denominator is the square root of x squared, so that's just an x. So we have the square root of x minus 1. Now we can take the derivative of x to the 1/2. This is 1/2 x to the minus 1/2. So this gives us 1 all divided by the square root x minus 1 times 1. And we can write our x to the minus 1/2 as 1 over root x. So we have 1 over 2 root x. And now what we're going to do is we are going to combine this square root with this square root. And we're going to write this as 1 all divided by 2 times the square root of x times x minus 1. And that's our answer. Hang with me. We have one more to go. We are going to take the derivative of inverse coth of secant x. We're going to use the chain rule again. Here is our outer function, and here's our inner function. Let's write down what our derivative is. This one is actually easier. The derivative with respect to x of inverse coth of x is 1 over 1 minus x squared. So we can say f prime of x is 1 divided by 1 minus, and then the x is whatever is our inside function, which in this case is secant x. So we have 1 minus secant²x in our denominator. And then we're going to multiply this by the derivative of secant x, which is secant x tangent x. Just going to draw a line here so we can see the right side from the left side. I think we might be able to simplify this. So I'm just going to write down the formula that I memorized. 1 plus tangent²x is secant²x. I always write down what I've memorized and then I rewrite it in terms of what we need. We need 1 minus secant²x. So 1 minus secant²x is minus tangent²x. So that's what we can put in for our denominator. This gives us 1 all divided by minus tangent²x, and then we have a secant x tangent x. So our tangent x is going to cancel, and then we're left with minus secant x all over tangent x. Secant is 1 over cosine, tangent is sine over cosine, so our cosines are actually going to cancel. So let's write this as minus 1 over cosine x on the top and sine x over cosine x on the bottom. And then we'll cross out our cosines because they cancel. So we have left minus 1 over sine x, and that is minus cosecant x. And that's it. You learned the definitions of the 6 hyperbolic functions explored important identities, and practiced finding derivatives. You also worked with inverse hyperbolic functions and saw how they connect back to logarithms. To really master all of these functions, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.